Okay, everybody, how's it going with your AP Calculus final review? I think in this video we're only going to do 2 or 3 problems, maybe 3 problems, and these are going to be area problems. So for 27, we've got the area of the region bound by the graph x equals y squared plus 4y, and x equals 0. So x equals 0, to start backwards here a bit, x equals 0 is actually the y-axis. And then this second function, x equals y squared plus 4y, that's going to be a parabola, but it's going to be a sideways parabola. I notice that the lead term is positive. So if you think about that, how that's going to go, that's going to be decreasing. The x coordinate's going to be decreasing, and then it'll reach a minimum. The x coordinate will reach a minimum, and then the x coordinate will start increasing. So we're going to have this shape over here. Let's take a look at the that function. We'll try to factor that out a little bit and try to find the zeros. Well, if you got x equals y squared plus 4y, well, then that's equivalent to x equals y multiplied by the quantity y plus 4, which means that x is going to be equal to 0 when y equals 4, when y equals 0, and then when y is equal to negative 4. Let's look at a graph. We're going to get x equals 0, which would be the y-axis. X is going to be 0 when y is equal to 0, which is right here, y is equal to 0. And then when y equals negative 4, which is right over here. So my graph is going to look something like this. My area is going to be trapped between that curve and the y-axis. So it's going to be this region right over here. This tells me that I'm going to have to use the left curve minus the right curve. I did that backwards. We have to use the right curve minus the left curve. The right curve is going to be the y-axis, which has the equation x equals 0. The left curve is going to have the x coordinates equal to y squared plus 4y. So when I put this together for an area integral, we're going to have the integral of 0 minus the quantity y squared plus 4y. Now the lower limit is going to be the smallest y coordinate in our region, which is going to occur right here at y equals negative 4. And then the biggest y coordinate, the top limit, is going to be here at y equals 0. So this is what our integral looks like. Let's clean up the integrand to make this look a little bit neater. Okay, that's going to make it look a lot easier for antiderivatives. Let's do our antiderivatives now. So we're going to integrate negative. So the antiderivative is negative 1/3 y cubed minus 2y squared. We're going to evaluate at negative 4 and 0 and then subtract the 2. Let's do that now. We'll substitute 0. So we're going to substitute over here. We're going to substitute our 0 and the other 0. Then we're going to subtract. Substitute negative 4. And then substitute the other negative 4. Okay. Let's take this and we'll evaluate all of the exponents. 0 cubed is 0. 0 squared is also 0. Negative 4 cubed is negative 64. Negative 4 squared is 16. Now we'll do some multiplication. All the zeros, of course, will multiply to make a 0. Let's see, negative 1/3 multiplied by negative 64. we'll just make that positive 64 over 3. And then 2 times 16 is 32, which I'm going to make 96 over 3 just to make it easier to subtract. Then now we'll do that subtraction. 0 minus 0 is equal to 0. And then 64 thirds minus 96 thirds, that's negative 32 thirds. And then, of course, 0 minus negative 32 thirds is just 32 thirds. Okay, well, that was one of these area problems out. Let's get this next area problem. We're supposed to find the area enclosed by the given curves. You've got y equals 2 sine x and y equals sine of 2x. Okay, so we've got some sine curves to graph. And we also have, thankfully, we also have this x has got to be between 0 and pi. So let's start with the easier one. We'll start with y equals 2 sine x. We know that's going to equal 0 at x equals 0 and x equals pi. We also know that it's going to reach a maximum at x equals pi halves. The maximum in this case, because of the 2, is going to be 2. So for the first curve then, let's do that in blue. That's going to be y equals 2 sine x. Let's just make this, and the y-axis, we'll make that 1, we'll make that 2. Pardon the really horrible handwriting. This is going to be negative 1 over here, and this is going to be negative 2. From 0 to pi, we only need really the this much of it, the left half, and sine is equal to 0 at 0 and at pi, and at pi halves, sine is equal to 1, so 2 sine is going to be 2. So this curve is going to look something like this. That's the easier of the two. Now, the other curve, sine of 2x, we're going to do a little solving here because we need to know when this curve is actually going to be equal to 0. The first thing to think about is that sine of 2x is going to be 0 whenever the angle inside of sine is equal to 0. Well, the angle inside of sine is going to be 2x. This is the angle inside of sine. So if 2x is equal to 0, sine of 2x will also be equal to 0. So we have the sine of 2x is equal to 0 when x equals 0. Well, the next place that sine of 2x is going to equal 0, that's going to happen when the angle is equal to pi. So when sine of 2x is going to be equal to 0 when the angle 2x is equal to pi, which means that sine of 2x is going to be equal to 0 when x equals pi over 2. Now, I haven't been keeping track over here. Let's go ahead and make our zeros. So we got a 0 here at 0. We've got another 0 here at pi over 2. And now we got to find, it looks like there might be another 0. And if you follow the pattern, I don't know why you wouldn't follow the pattern, it looks like the next 0 is going to be at pi. So let's make sure. The next time that sine is equal to 0 is when the angle is going to equal 2 pi. So in this case, since our angle is 2x, we've got to make 2x equal to 2 pi. And that would mean that the sine of 2x is equal to 0 when x is equal to pi. So that does follow the pattern over here at pi. Let's draw our curve. We know that halfway between 0 and pi halves, that's at pi over 4, we're going to get a value of positive 1 because that's the way that the sine graph works. And then halfway between pi halves and pi, we're going to get a negative 1. So This is going to help us find our shaded region. Our shaded region is going to be the area here between our blue curve and our green curve. And nicely, our top curve and our bottom curve are never going to change. Our top curve is always going to be blue, and our bottom curve is always going to be green. So we just need to integrate the blue curve minus the green curve from 0 to pi, and that'll be our area. So our integral in this case is going to be the integral from 0 to pi of the blue curve minus the green curve. Let's remember that the blue curve is 2 sine x, and the green curve was sine of 2x. And we are underway for this integral. Let's get our antiderivatives. The antiderivative of sine 2 sine x, that's going to be negative 2 cosine x. And then our antiderivative of sine of 2x, that's going to be negative 1/2 cosine 2x. So we're going to minus negative 1/2 cosine 2x. And we're going to evaluate this antiderivative from 0 to pi. All right. Let's do some substitution. First, we're going to substitute pi minus, now we're going to substitute 0. Great. Let's take this and let's evaluate our trig functions. See, cosine of pi is negative 1. And now cosine of 2 pi is 1. Moving on to the next subtractant, the cosine of 0 is 1. And then over here, 2 times 0 is also 0. And the cosine of 0 is still 1. Now we'll do some multiplication. Let's do some addition now. 2 plus 1/2, that's 5 halves, I believe. And then negative 2 plus 1/2, I think that's negative 3 halves. And then now 5 halves minus negative 3 halves, that's 8 halves, or just 4. Well, hey, that does it for question 28. Let's take a look at 29 now. We're getting to cross-sectional areas. So the base of a solid bound by the graphs of x equals y squared and x equals 4. The cross-sections are perpendicular to the x-axis, and they are triangles with an altitude of 2. So let's not look at the cross-sections just yet. Let's just figure out the base of the solid. We've got x equals y squared and x equals 4 as our bounds. X equals y squared is a parabola that is opening to the right. Rather than give you an ugly graph, I thought we would go with Desmos and give you a nice looking graph. Now the next part here, now that we have that, let's write down the word base here so we know that this is the base. We know that the cross sections are perpendicular to the x-axis. So here in red, I'm going to draw the footprint of one of those cross sections. Okay, so the length of this we're going to need to know. It's going to be from the y coordinate up here to the, actually I don't know if you can see my cursor, but we need to know from the y coordinate up here to the y coordinate down here. So we're going to have to get the y coordinate here is going to be on this upper half of the parabola. And up there, we know that y is equal to the square root of x. Yeah, that's going to be our upper root. Now at the bottom over here, this is going to be y is going to equal to the negative square root of x. And so if the length of this cross-section goes from y equals x to y equals square root of x, then the length of that footprint is going to be square root of x minus negative square root of x, which is the same thing as 2 square root of x. Okay, so also we can see that the x minimum is going to be 0, and the x maximum here is going to be 4. Remember that our cross sections are perpendicular to the x-axis, which means that we're going to have an x minimum and an x maximum for our limits. Let's deal with the cross sections now. The cross sections are triangles with an altitude of 2. So we need to get the area formula for a triangle. So here's our cross section. Our cross section is going to be a triangle. In red here, I have my length L, which we know is 2 root x. Now we just got to get the area of this cross section, and if we know that the cross section is a triangle, well then we know that the area of that cross section is 1/2 base times height. Now the base of this triangle is going to be L. And the height of this triangle, well, it says that the altitude is always 2, so the height is going to be 2. In other words, the area of this triangle is always just going to be L. And if you remember from earlier, L was equal to 2 square root of x. Right over here, L is 2 square root of x. So now we have everything we need in order to get the area of this region. So the area is always equal to the integral from a to b of the area formula. We know a is 0 and b is 4. And we know the area formula is 2 square root of x. Remember, that's right over here. Area is 2 square root of x. And over here, a and b are 0 and 4. So now this gets to the calculus part. This is actually the easiest part of this entire thing. Let's find our antiderivative of 2 square root of x. Well, square root of x is x to the 1/2, and 1/2 plus 1 is 3/2. So the antiderivative is 2/3 x to the 3/2. And we're going to run this from 0 to 4. Well, it'd probably help if we simplified what we have here. So 2 times 2/3, that's 4/3. And then x to the 3/2, that's the square root of x cubed. Okay, so 4/3 square root of x cubed. Next thing we're going to do is, let's substitute 4 and 0. Then we can evaluate these. Let's see, the square root of 4 cubed is, that's 4 times the square root of 4, so 4 times 2 is 8. And then, of course, the square root of 0 cubed is just 0. And then we'll multiply. 4/3 times 8 is 32/3. And then 4/3 times 0 is 0, which means my area is just 32/3. Which completes this problem. Well, all right then. I think this is about as much as I wanted to get done, I think. And that's where we're going to close it for today. We'll see you next time here for more of this math.